My name is Matthew Cruz, and I am incredibly excited to talk to you today about writing a dictionary with F Sharp that is the fastest dictionary in .NET. Now, one of the things I want you to take away from this talk is the thought process and tools that we use for optimizing data structures. This is just one particular example, but this could be applied against all types of data structures. Now, another name for this talk could have been an engineering experiment that got out of hand because it ended up going much farther than I ever intended it to do. Now, for a little bit of context, who am I? Well, I am a software engineer and I work for Simulation Dynamics. Simulation Dynamics is a consultancy based out of the United States that works with predominantly Fortune 500 companies to build simulations to optimize supply chains, warehouses, and manufacturing facilities. And we are a .NET shop with quite a few F Sharp developers, actually. In addition to that, I also run the Fast F Sharp YouTube channel, where I provide introductory material to learning F Sharp, but then also provide deep dives on how to optimize the performance F Sharp so it can run as fast as possible. And I also do some consulting for other companies as well as they need F Sharp performance improvements. Well, the story begins with me taking some time just kind of pondering. And I'm like, I wonder what the performance is of the different key value collections in .NET. So things like dictionary, read-only dictionary, the F Sharp map. And the reason I was curious about this is because one of the patterns that I often use is I have a static set of data that I want to perform frequent reads on. And so I want those lookups to be as fast as possible. But since the data is static, I put it in a read-only dictionary so I know that my program is not mutating that data later on. So out of curiosity, I decided to create a benchmark for this test. And the benchmark was going to be looking at two different possible key types, integer and string. Now, in reality, I actually tested a lot more than this, but for the purposes of this presentation, I'm going to limit it to integers and keys because I only have an hour. And there's only so many different charts I can show you without overwhelming you. I'm also going to use sizes of 10 keys, 100, 1,000, and 10,000. And again, in reality, I actually tried a bunch more, but these were the sizes that provided the picture I wanted to paint for you. So what is the actual thing that I am measuring? Well, it's going to be the sum of the time to perform 100 random lookups on 100 random instances of these key value collections. And the idea behind this was I didn't want the CPU to be able to memorize access patterns or memorize the data. I wanted it to have to struggle with the randomness of looking something up in a key value collection, like a dictionary. And I decided to start with the default collections available in F Sharp. So the F Sharp map, the .NET dictionary, the read-only dictionary, F Sharp dict, and F Sharp read-only dict, which are convenience functions for creating these key value lookup collections. And when I measure that, this is the picture I get for integer keys. And what we see is that the F Sharp dict is faster for 10 and 100 keys, essentially the same performance for 1,000 keys to the .NET dictionary, and again, similar for 10,000. When I go to string, though, the .NET dictionary is faster for string keys across the board. Now, one of the things you might notice is that the read-only dictionary is not as fast as the plain .NET dictionary. And I actually found this a little bit upsetting. And the reason is because I realized I'm paying a performance penalty for using a read-only dictionary instead of a plain .NET dictionary. And in my mind, that didn't make sense. Why would that be the case? Shouldn't a static set of data be able to give you better performance than a mutable set of data? So I decided to start doing some research on what it takes to write a fast dictionary. And on my journey, I came across this fascinating talk by Malte Shrupke. I hope I am pronouncing that correctly. My apologies if I am not. This is a C++ talk where he showed that it is possible to create a hash table, which is another name for a dictionary, that was dramatically faster than the default dictionary in C++. And I found this very interesting because I had always assumed that the C++ crowd is obsessed with performance. So wouldn't their default dictionary have the maximum possible performance? And what Malte showed in this talk is that that is not the case at all. And in fact, there are huge performance improvements that can be made to the default dictionary in C++. So that got me thinking, what if the dictionary that is built into .NET is not actually fully optimized? What if we could actually implement something that's even faster than the .NET dictionary? So I decided to take on what felt like an overwhelming task at the time. And this is an actual picture of how I felt, me kind of battling Cthulhu. And the challenge I set out for myself was I want to see if I can build a better dictionary than .NET. And what I mean by better is faster for reads. I want to put in a caveat here at the beginning. The .NET dictionary is fantastic. It is a great dictionary, so I'm not going to speak ill of it at all. It protects you against problems that you probably don't even realize that you have. Things like frequent collisions for strings and denial of service attacks. So it is a great dictionary, but I wanted to see if I could create one that was faster. And the idea I had was, let's start with something very simple. And then over time, I will evolve it using profilers and benchmarking. And then hopefully by the end, we could come up with something pretty awesome. So this is hopefully a visualization of what the end product of this is going to be. So to start off, I said to myself, let's start with a completely naive implementation of a dictionary with no regard for performance to have a starting place. And if you go and read the literature on dictionaries, also known as hash tables, you will see that what is often done is that you have this array, often called buckets. And this array is kind of the backing data store for your keys and values. And the way you insert a key and a value into the dictionary is that you start with the key and the value. You then compute a hash code based on the key. So you're taking that key, which is some arbitrary type, and then you have some logic for turning that into an integer value. Hash codes in .NET are almost always modeled as integer 32. So when I say hash code, I'm referring to a random int 32 that key transforms into. I then take that hash code, and then I have logic for mapping that hash code to a bucket in this backing array. Now, for simplicity, the way you can deal with collisions is you don't put your key and value in the actual bucket itself. The bucket has a reference to a linked list that sits out on the heap. So that hash code gives you the pointer to the list. You then follow the list and then add your key and value to that linked list. So that means when you want to add another key value pair to this dictionary, you again compute a hash code. That hash code maps to a bucket, and then you follow the linked list and add an element to the end of it. This technique for dealing with collisions in dictionaries is called separate chaining. And it's the naive beginner's approach to doing this. And so what does that look like in our code? Well, we're going to have a type bucket, which holds a key and a value. And then when we create our dictionary, we are going to create a buckets field. And that is an array, which is holding lists of buckets. In this case, the list in F# is a linked list. It's not the list from C#. It's a very different thing. So what is the logic that we then use for mapping that hash key to a bucket? Well, in this case, we're going to use the F# generic hash function, which can take some arbitrary type and compute a hash for it. We then want to mask off the first bit of that int32 to ensure that it is positive for our case. And then we use the mod operator to take that arbitrary int32 and map it to one of the buckets in our backing array. So how do we then search for key values once we've inserted all the ones that we want to store? Well, we would compute the bucket index for that key. We then find the linked list in the array. We're going to use the F# list.find function, which searches for an element that returns true. And our condition is going to be using the simple and default equality logic for types. When I use this approach, the performance is terrible, which is to be expected. This is the naive approach, no regard for performance. So for integer keys, it is terrible across the board. So we only have room to grow from here. For string keys, it's not quite as bad, but we are still far behind. Now, the way we are measuring all this is that we are using the fantastic library BenchmarkDotNet, and it is able to report various metrics on how our benchmarks are running. And one of the things that we find is for our benchmarks that we are performing a lot of allocation while doing lookups in a dictionary, which is absolutely outrageous. And this is what it looks like inside your CPU when you have allocations occurring inside your dictionary lookups. It is not a good thing. It is terrible. So how do we deal with this situation? Well, I use .memory, and I start looking at the heap, and I start looking at the allocations, and I'm saying, where are these allocations coming from? What is going on? Well, what is going on is that the code is using the built-in hash inequality to F# that is robust, but it is not fast. So we want to get rid of that, because remember that I mentioned we're using this generic hash function that's built into F#. That hash function can take types of arbitrary shape, but because of that, it's not necessarily fast. So we want to replace it with something else. So what do? We go back to this naive approach, and we need to get rid of this hash function. We are instead going to use the equality comparer default get hash code. This will remove the allocation that is happening when we do the hashing. And then we go to our lookup logic, and we want to get rid of this equality. This is another location where these allocations are coming from. We instead want to use equality comparer.default equals. And this will get rid of the allocations happening when we are doing the lookups. So now when we use this updated version of our dictionary and we benchmark that, we see that integer keys are now performing dramatically better. On this chart, the .NET dictionary is in blue. The dictionary that we are evolving will always be in orange. And the previous version's performance will be the green bars. And so you'll always be able to compare what the performance was like compared to the previous version of our dictionary. So we're going to be constantly evolving this. So now our integer lookups are dramatically faster in this case, and we'll discuss why later. And strings are now faster for 10-element and 100-element dictionaries, but slower for 1,000 and 10,000. Sorry, slower than the .NET dictionary. So I continue doing research, and it turns out that Malti, the person who gave that talk that inspired me, actually has a blog where he has incredibly detailed analysis of the work that he did optimizing a dictionary. And one of the things that he talks about in there is the idea of Fibonacci hashing. And he proposes Fibonacci hashing as a way of mapping hash codes to buckets that is faster than using the mod operator. Let's talk about what that looks like. So right now, when we map a key to a bucket, we are using this mod operator. And this is a very, very common technique. And if you actually go look in the .NET source code, they have a fast mod function. So again, very common to use this because it makes it very easy to map an arbitrary integer to a an array of any given size. Now, rather than that, we're going to use the Fibonacci hashing, and this is what Fibonacci hashing looks like. We now have this large number, which comes from, if you want to understand the math of why this works and why it's good, I recommend going and reading that blog post because he does a fantastic analysis. But instead of the mod, we're going to multiply by this very large number, which has very good randomness properties. That's going to cause the integer to overflow and generate a random integer. And then we're going to use a bit shift to map that large integer down to a power of 2. And the restriction that we are now adding to our dictionary is that the size of that buckets array that's holding our data has to be a power of 2 for this technique to work. Now, why would we want to do this? Why is this such a good idea? When you want to do mod in any language, that maps down to the idiv x86 instruction. And if you go and look at the logic that has to happen in the CPU to do division, it's very difficult. CPUs are terrible at division, and it's beyond the scope of this conversation, but it's not possible to make it fast. So when you're doing a mod, you're actually doing an idiv x86 instruction, and that has a latency of 13 to 28 CPU cycles. So it takes 13 to 28 cycles before the next operation can commence. Compare that to Fibonacci hashing, which uses the imul instruction and a shift right. Together, those are only 4 CPU instructions. So Fibonacci hashing is anywhere from 3 to 6 times faster for mapping a hash code to a bucket. So this optimization gives us another boost in performance. We now see that Fibonacci hashing is dramatically faster than our zero allocation version for dictionaries with 10 and 100 integer keys, but essentially the same performance for 1,000 and 10,000 element dictionaries. When we go to strings, we do see a slight boost in performance. It's more dramatic for 10 and 100, and it's less so for 1,000 and 10,000. So let's go look at our benchmarks coming from BenchmarkDotNet. And one of the reasons that integer lookups are doing so well for our small dictionaries is that the CPU is so smart looking at our data and our access patterns that it is able to almost perfectly predict the branches that needs to be taken. So that is why we're getting this astounding performance from integer lookups already. Now, I got curious and I said, I saw a dramatic improvement for integer, but I didn't see a dramatic improvement for strings. So the question I had was, why are string keys so fast? What is going on in the .NET dictionary that makes them so good? So what I decided to do is to use dotTrace and profile my own program to say, where is my program spending so much time? And I see that it's spending a significant amount of time on this compute hash 32. And this is the logic that it's using for hashing the string. So I said, okay, well, let's see what .NET is doing in this case. So I dig into the source code of .NET, and I find this code in the .NET dictionary, and there's some really interesting comments in here. One of them is that it is storing the comparer for ref types. So that's an optimization that I could include. I also see that for value types, it's always using the default equality comparer. And this is so that the JIT can inline and devirtualize for value types. So again, a fantastic optimization. I think I'll borrow that. But I also see this really interesting thing. I see that's checking the key type, and it's doing something special for strings. And you see this all over the .NET code base. String is such a predominant thing that you will often find unique optimizations involving string. So I keep going down the rabbit hole and say, okay, where's the actual logic for computing the hash of a string? And I eventually find this. So this is the special logic that the .NET dictionary is using for hashing strings. And it is extremely performant piece of code. And I said, I like that. I think I'll borrow it. And by borrow it, I mean, translate it to F# and use it in my own code because it's such a good idea. So this is the F# version of that code where I've just translated it to F#. And so I'm going to use this as my equality comparer for string types. And then when I create my dictionary, I'm going to have a check on the key type, say if it's string or not. And if it is, I'm going to use my string comparer. And when I use this, I get an interesting result. It is slower for 10 and 100 element integer dictionaries and barely faster for 1,000 and 10,000. For strings, it is just as fast for 10 and 100 element dictionaries and faster for 1,000 and 10,000. And it's at this point I get an idea. Now, I remember doing some light metaprogramming in .NET back in the day because I knew that the runtime and the JIT could look at your collections and figure out what pieces of code will never actually be hit and can simplify your code so that it actually runs faster. So I said, okay, up to this point, my get value function has had the type check inside of it. So this is kind of way buried down deep into the dictionary itself. I said, well, why don't I raise that type check higher up in the dictionary? So now I have two functions, one for getting struct values and one for getting ref values. And then I have this type check at the very top. So it's right next to where the code is for actually indexing into the into the dictionary. And what result do I get? No difference. No change at all for integers and barely any difference for string dictionaries. So this is where I have a warning. What I find so fascinating about this is that optimization actually did something pretty significant in .NET 6. This code is all being tested with .NET 8. So the warning is just because an optimization yielded something on previous versions of .NET, that does not necessarily mean it is going to give you a boost in future versions of .NET because it is constantly evolving. So now we need to go back to BenchmarkDotNet and figure out what's going on. What can we do to improve the performance of our dictionary? Well, one of the things that I notice is that for the large string dictionaries is that we have a significant number of cache misses. And a cache miss occurs when the CPU needs to work with a piece of data that does not fit within the caches of the CPU, so it has to go all the way out to main memory to read that information. That might not sound bad, but reading from main memory can take over 200 CPU cycles. So your program is sitting dead waiting for this data to come in. And if there are a large number of cache hits, it is extremely expensive for your performance. So I would like to have a different way of laying out my memory, which reduces the cache misses. So one approach to this in the literature is to use the idea of linear probing. Up to this point, the actual keys and values of our dictionary were stored in linked lists. Now what we are going to do is we're actually going to embed the key and value in the buckets array itself. How do we do with collisions though? So if I have this new key and value that I want to insert, I'm computing the hash code. That hash code maps to a bucket. There's already a key and value in that bucket. So I need to find a spot to put them. So what I do is I search down the array in a linear fashion to find the next available slot. And I will insert it into that next spot. So this approach of embedding the keys and values in the array is called open addressing. So how does this change our code? Well, now bucket is going to have key and value, but we're also going to include hash code because when we're comparing equality of strings, that can be very expensive. So what we're going to do is before we check the equality of string, we're going to say, do the hash codes actually match? If the hash codes match, then we'll check for string equality. But if they don't match, there's no way that the strings are actually equal to each other. So we're embedding all three of those elements into each bucket in our buckets array. How's the performance of this? Well, again, mixed bag. For integer keys of 10 and 100 element dictionaries, it is terrible compared to Fibonacci, which has been our best to date. For 1,000 and 10,000 element dictionaries, it is actually better. When we go to benchmarks, you'll see why this is happening. But notice that there's a huge performance difference here. For strings, though, we get a more interesting result. Linear probing is worse for the 10 element dictionaries, but faster for 100, 1,000, and 10,000. So if we go to BenchmarkDotNet, we can see the reason that integers are performing so much worse than they did in Fibonacci is that our branch mispredictions have gone up dramatically. This is very bad. But don't worry, we'll get that performance back by the end. But we can see that the number of cache misses for our string dictionaries has gotten significantly better. And that is why we are getting better performance. Now, let's talk about one of the problems that can occur with this linear probing technique. I have an existing dictionary. It has its buckets array. It has quite a few key value pairs in it already. I get a new key value pair. I compute the hash code, and I map that to a bucket. That bucket already has a key and value in it, so I start searching. Next bucket, still full. Next bucket, still full. 100 entries later, I actually find an empty spot to put this key and value in. And so what does this mean? Using linear probing naively, it is entirely possible that the key can be very far from the bucket it originally mapped to, which means the worst case performance for linear probing can be very, very bad. And this is part of what is kind of causing these these branch mispredictions for those integer keys. And so we would like to have an alternative layout that keeps the data closer to where it originally mapped to. And one of the techniques that's used for this is called Robin Hood hashing. Now you notice in our buckets, we've added a piece of data, and that piece of data is the offset. What the offset represents is how far is that key from the original bucket it mapped to. So in this case, key 1 and key 2 are actually in the bucket they originally mapped to because their offset is 0. Okay, how does Robin Hood hashing deal with collisions? We have key 100. We compute the hash code for it that maps to a bucket that already has a key and value in it. If we were to insert key 100 into this bucket, its offset would be 0 because it's the first bucket it mapped to. Key 1 is already in that bucket and also has an offset of 0. We have a tie. So we don't evict key 1. Key 100 has to go somewhere else. So we go to the next bucket, kind of like linear probing. But this is where it's different from linear probing. Key 100 would have an offset of 1 at this location. Key 2 has an offset of 0. You can think of key 100 as being poorer. It is worse off than key 2 at this location. And so what we do is we evict key 2 and we put key 100 in. And this is the idea of Robin Hood hashing. It comes from the legend of Robin Hood, which was a person who stole from the rich and gave to the poor. And so the idea here is that we are going to steal from keys that are rich and that they are close to their home and give to keys that are far from their home. So we've evicted key 2. We're going to have to reinsert it, and it goes into this next available slot, and its offset is now 1. And so the idea with Robin Hood hashing is we're balancing out just how bad off any key value pair is and trying to keep things relatively close to the original bucket that they map to. And the idea is that we're going to have to iterate through fewer buckets in the worst case scenario. So how does this change our code? Well, now bucket has 4 elements. One of them is the offset, which represents how far that key is from its home. How does this do? Turns out it is worse across the board for integer keys. Interesting. It is also worse for string keys across the board. What is going on? Great question. And again, BenchmarkDotNet reveals our branch mispredictions are worse across the board. And the reason for this is that with linear probing, there's a high probability that many of the keys were actually in that first bucket they mapped to. But with Robinhood hashing, you're often evicting keys because you're trying to prioritize things being close to their home. And so this ends up causing more branch mispredictions. So your worst case scenario may have theoretically gotten better, but your average case has gotten worse because the CPU is having a harder time figuring out what logic it needs to follow. So one of the lessons that we need to take away from here is that performance is this balancing act. We have to consider, are we trying to optimize the average case? Are we trying to optimize the worst case? The correct thing to optimize for will depend on your use case and what the demands of your application are. In my case, I'm trying to optimize the average case. And so this is no go for me. Now, if you're curious, there are many other approaches that fall under the open addressing approach. Things like quadratic probing, double hashing, cuckoo hashing, hopscotch hashing. Turns out this is a pretty good place to get a PhD, apparently. But what I'm going to do now is skip to the ultimate version that Malti gave in his presentation. Malti also wrote up a blog post where he detailed the engineering that went into his ultimate version. He called it a byte linked list. I'm going to call it a byte list because the list in F# is a linked list. And I didn't copy his code exactly. I was basically inspired by his approach, but I had to adapt it considering that F# has a different set of restrictions than C++. So how does a byte list work? Well, when we want to add a value to a byte list version of a dictionary, we again have our key and value. We compute their hash code. We map it to a bucket. That bucket is currently occupied, so we can't insert it in there. We search for the next bucket, still occupied. We go to the next one. It is available, so we will insert it in here. Now, this is where byte list is different than those other approaches. We're going to go back to the original bucket that key 3 mapped to, and we're going to add an entry, and we're going to call it next. And what next represents is the offset to the next key that mapped to this bucket in the first place. And so these next fields are acting like indexes of a linked list that has been embedded in this backing array. So this means when we want to go look up a value from this dictionary, we again start with the key, compute its hash code, we go to the original bucket that it maps to. We check, does key 1 match key 3? It does not. And instead of doing what linear probing or Robinhood hashing have to do, just iterating through the buckets one by one, it can immediately skip to the next bucket that could possibly match this key. So how does it change our data? Well, now we have our bucket and we have this next field and we're storing it as a byte. And the reason we're storing it as a byte is because it's small and the probability of your offset being greater than 256 is infinitesimally small. Now, you obviously have to do some programming to protect against degenerate cases, but it essentially never happens. So what is the performance of the byte list? Dramatically faster. Dramatically faster. This is by far the fastest thing we've seen so far. So this is fantastic. I told you we would get that performance back. So wonderful times. Same thing goes for string. String is now faster than the .NET dictionary across the board. And so this is just a win everywhere. And at this point, I was very excited and I thought I had done well. And I want to emphasize, I'm not doing anything particularly innovative here. I'm just being inspired by developers in other fields who are actually far smarter than me and then translating it to F#. So I'm not taking credit for these ideas. I'm just being inspired and seeing what it looks like in F#. I felt good for a while. And then a new foe appears. And that foe is the FrozenDictionary. Now, coming in .NET 8 is the frozen collections, one of which is the frozen dictionary. And the idea is let's have some collections that are optimized for read access. We will front load the creation of these collections by doing some additional work to ensure that the read performance is as fast as possible. So Frozen Dictionary was created for the exact scenario that started this entire project. And I was like, okay, well, let's see how Frozen Dictionary does against what I have so far. And when I compare it for integer keys, I'm still feeling pretty good. Byte list is still faster in this case. I'm like, oh, and to be clear, Frozen Dictionary is now the blue bars. Byte list is the orange bars. And so it's no longer the .NET Dictionary. This is Frozen Dictionary as the blue bars. When I compare it to string, though, things change slightly. Byte list is faster for 10 and 10,000 element dictionaries, but it is slower for 100 and 1,000. Okay, what are we going to do here? Well, again, we are guided by benchmarks. We're not guessing where the problems are. We're measuring where the problems are. And BenchmarkDotNet is saying, hey, you actually still have quite a few cache misses when performing these lookups. And so I thought to myself, what can I do to improve the data locality for these and reduce those cache misses? And this next idea actually came from the game industry. So the game industry is often writing code that has to run as fast as possible. And so one of the things that they will do is they will lay out their data in a different way. Up to this point, the way we have been laying out our data would be referred to as an array of structs. Buckets is an array. Each element in buckets is a struct. That struct is made up of several fields. Very common way of laying out data. An alternative way of laying out data would be a struct of arrays. So those fields in our struct now become arrays themselves. And so you can think of this as actually pivoting your data and reorienting it. Now, why would you do this? And I want to be upfront. This is not always a win. The use of this technique really needs to be guided by your use case and how your program runs. But it is often a good optimization, so it's something to consider. And so what does this make our code look like now? Well, now we have this type data. And so this is the data contained by our dictionary. Keys is now a string array. Values is now a value array. Hash codes is an integer array. And nexts is a byte array. So we've basically taken the byte list implementation and done a struct of arrays transform on how that data is laid out. For integers, it's worse. It's worse across the board. So what this tells you is that, oh, okay, maybe I don't want to take this approach. Maybe this is actually worse off. I thought this would help things. For the case of integer keys, it does not. For string keys, though, it gives us a significant improvement, almost universally. I mean, the improvements for 1,000 and 10,000 element dictionaries is smaller, but it's still there. So one of the things that we should take away from this is that, hey, if you're wanting to write a really optimized data structure, you may have to have alternative layouts based on the types going into that data structure. So this is actually something that .NET already does with its dictionaries. So I don't consider this a thing cheating at all, but it's something to consider when you're trying to push performance as hard as possible. Now, there still remains a problem. My version is not as fast as Frozen Dictionary for 100 element dictionaries. And I get a little depressed, I'm not going to lie, because I knew that the JetBrains.NET days was coming a ways out. And when I started this project, I'm like, oh, this would be a great talk for them. But then when I came across this, like, I can't make this claim about being the fastest anymore. So what is even the point? So, and I struggle with this, and I try so many different things and I make zero headway. And I'm like, what on earth is Frozen Dictionary doing that is making it so obscenely good? And so I went deep into the Frozen Dictionary and what the heck is going on. And it turns out the reason Frozen Dictionary is scorchingly fast for this scenario comes down to the idea of perfect hash functions. What is a perfect hash function? A perfect hash function is a function that can take a set of keys and map those keys to a set of buckets with zero collisions. It is guaranteed to not have any collisions at all. And when you can guarantee that, you don't need logic for dealing with collisions anymore. You don't need search logic to start iterating through an array and find where the problem is. Find where the key is in some alternative location. And what is happening with Frozen Dictionary is that when you bring in a set of keys to create the dictionary, the first thing it does is it examines all those strings. And it will emit the most optimal hash code logic possible for those strings. And it will do crazy things like use the length of the string as a hash code, use a single character of the string as a hash code, use the minimal subset of the string for the hash code. It's a very impressive piece of engineering, I'm not going to lie. But it is essentially creating perfect hashing functions every time for dictionaries of 100 elements. Now, it's not guaranteed in their code, but it is essentially what is happening at the end of the day. Now, why is creating a perfect hash function a difficult problem? Well, it comes down to the idea of the birthday problem. What is the birthday problem? The birthday problem is a very interesting product of probabilities. And it's the idea of how many people do you need to get into a room before two people actually share the same birthday. And what is a very surprising result is it only takes 23 people to get together for the probability of two people to share a birthday to be 50%. It's bizarre, but it's true. And so this idea of birthdays colliding and having a very high probability of collision also comes up with keys mapping to hash codes, mapping to buckets. And that's why it's a really difficult problem. And so I probably thought about this for a month, maybe longer. And I didn't take snapshots of my notebook where I just started scribbling out ideas like, is it possible for me to create a perfect hashing function that is also fast? It's not difficult to create a perfect hash function. You can do that. That's not the issue. It's when you need that perfect hashing function to be fast that you run into a whole bunch of problems. And so I mulled over this, and then I had this thought. What if the hash codes for the dictionary are unique? What if we add this restriction to our data? What does it enable for us? Well, let's talk through a possible scenario, and I'm going to start describing an algorithm. I was not able to find it in the literature. If you are someone who's watching this live or is watching a recording and you know what this algorithm is that I'm going to describe, please email me. I would like to know because I would like to give credit. And this technique is not guaranteed to work every time, but I haven't seen it fail yet. I'll put it that way. The probability of it succeeding is very high, and it has to do with the guarantees of randomness when it comes to hash codes. So let's say I have this situation. I have 5 keys with 5 hash codes mapping to 4 different buckets. Key 1 and key 5 are not a problem. They've each mapped to a unique bucket. But I have to deal with the collisions of keys 2, 3, and 4. And now remember, I have guaranteed that the hash codes are unique at this point. So assume that has taken place. And this is one of the other things that's important about this technique. It's not guaranteed to succeed. So you need a fallback version of your dictionary to deal with the scenarios where you do have hash code collisions, where 2 keys are computing the exact same hash code. Highly improbable, but possible. You need to deal with it. But let's assume we've done that validation and we have unique hash codes. And for this example, let's say these are the hash codes for those keys. So key 2 has a hash code of 38889, Key 3, key 4. They are unique. Now let's represent those hash codes as binary, so just zeros and ones. If I want to differentiate between three keys, I need at least 2 bits of information. And that's kind of intuitive. If you want to differentiate between 2 keys, you need 1 bit because a bit can be 0 or 1. If you need to differentiate between 3 keys, you need 2 bits. So that you could have 0, 0, 1, 0, or 0, 1. So we need at least 2 bits of information from these hash codes to uniquify them from each other. So what I mean by that, like, hey, there are several candidate locations. I'm looking for locations in these hash codes that will uniquify the hash code based on just 2 bits. And these are examples of what I'm talking about. You see that first one where you have 0, 1, 1, 1, and 1, 0. And then there's several other places inside the hash codes where this is also true. I'm going to use these 2 bits as the uniquifier for these keys. And so what I'm going to do is I'm going to take this location. I am then going to shift it to the right by 26 locations. Then I am going to mask off any extraneous bits that I don't need because I only want those last 2 bits at this point. So I use a mask to get rid of them. And now I reinterpret those hash codes as just an offset. So now I know, hey, key 2 has an offset of 1, key 3 has an offset of 3, key 4 has an offset of 2. Now let's talk about how we use this information. Our dictionary now has 2 arrays. One array contains the shifts and the masks, so just what we just walked through. And the second array is the actual buckets containing the keys and the values. So if I want to look up a key using this, if I want to look up a value using a key, using this logic, I'm going to do the following. Let's say I have key 2. It gives me hash code 2. That hash code is still mapping to that second bucket like it did before. And now I know I can use what I'm calling the start index to say all of the keys that map to this bucket, their values start at this location in the buckets array. So this is a way I can store all the different values in one contiguous array is I'm using the start index to say, hey, every key that mapped to here, their values actually start here in the buckets array. Then I use the bit shift and mask that I just described to compute the offset associated with that hash code. And this is a way of being able to deal with collisions because I'm first taking the keys, mapping them to this intermediate array, and then figuring out, okay, what are all the hash codes that mapped here and what bit shift and mask do I need to use to uniquify them? And that is then what I will use to do an offset in the buckets array, which actually contains my keys and values. So how does that look in my data? I have this shift and mask type. I have my bucket still. In this case, I'm just talking about the string dictionary. So the key is just string, but again, you can make this generic. And then I have my data, which has a shifts and mask array and a buckets array. Now, when I use this technique for integer keys, it's worse. It's worse across the board. So this is an example of where like, okay, creating this like special logic for uniquifying things, it's not as fast. And it's because the byte list is just so good when it comes to memory layout and being able to index into it and look up data. So this is not a win when it comes to integer keys. When it comes to string keys, though, it is faster across the board. And now we are actually faster than the FrozenDictionary with string keys across all cases. Oh, so this is what my face looked like after I got through that. I was pretty ecstatic. So based on this, what are the next steps? Well, first of all, I want to be upfront with you. I started testing these versions of the dictionary against the benchmarks that are in .NET. The versions I have win in most cases, but not all. And for me, if I want to contribute this type of thing to the .NET code base, I want to make sure it's winning across all cases. So I do have some gaps to fill in there. Like I said, it's faster in a majority of cases, but not all. And if that ends up being the case, if I'm able to close that gap, I would look into seeing if I can contribute to .NET. It'll be interesting because everything in .NET is written in C# and everything I wrote is in F#, but we'll see. In the meantime, though, one of the things that I've been working on is collecting all of these high-performance collections that I use into a single library called idos.collections. And the reason I call it IDOS is because IDOS is the name of our discrete rate simulation engine that we have developed at Simulation Dynamics, which is the fastest discrete rate simulation engine in the market. And there's quite a few specialized collections that I use for these high-performance scenarios that make writing this kind of code much easier. And so this version of the read-only dictionary would actually go into that collection. And the reason I want to do that is because I already have someone who's actually like taken my code to use in their code base. I'm like, bro, this is not production ready. And he's like, I know, but I'm stuck on .NET 5 and I need something. I'm like, oh, okay, because FrozenDictionary isn't coming to older versions of .NET. So at the very least, I can put this out there for people who are stuck on older versions of .NET and won't have access to FrozenDictionary. So what are the lessons I am wanting you to take away from this talk? One of them is that I want you to benchmark, don't guess where your performance problems are. You should always be measuring. You should never just be assuming whether an optimization is going to be better for you or not. I hope that you've learned that because I showed you several cases where we had an optimization that we thought would yield something and it ultimately didn't. So make sure you're measuring, not just guessing. And you should be letting the profiler and hardware counters guide you as far as what you need to do to improve performance. And you may need to optimize your collection based on the type of data that it's storing. The ultimate version of this uses a byte list version for integer keys and this perfect dict function methodology for string keys. And then for ref types and struct types, I might use something alternatively for a better memory layout. But consider that that's the price you're going to pay when you want to take ultimate performance. You may have to have specialized versions based on your use case. Also, .NET performance is always evolving. And just because an optimization worked in a previous version of .NET does not mean it is going to yield you something on a future version of .NET. And I was actually really delighted with this because it saw that the optimization that I had used previously that involved more work were no longer necessary because the JIT compiler is so good now at figuring out what it is your program is trying to do. And lastly, don't assume that everything out there has already been optimized. The computer science field is still a very young art. And in reality, like how long have we been programming computers? Not even 100 years. And so don't think that things are necessarily settled and something is actually optimal at this point. And part of that comes down to the fact that hardware is still rapidly evolving. We are now seeing this proliferation of different types of hardware. It's not just CPUs, it's not just GPUs. We have things for neural networks and all kinds of sophisticated things. So just because one technique is optimal in one use case does not mean it's optimal for your use case. And so finally, I just want to say thank you. Thank you to Multi. If you ever see this, your talk and blog were incredibly inspiring. Thank you also to the F# community for your patience with all of my crazy questions. And also thank you to JetBrains for hosting me. If you enjoyed this and you want more of it, I actually have a 14 video series on my YouTube channel where I go into much greater detail and go much slower unpacking the code, the benchmarks, and the profiling. So if you wanted to learn more, I suggest you go check out that channel. So thank you very much for having me today. It's been a real delight to be speaking. And again, if you have questions, feel free to email me and contact me and ask you questions. And if you have a performance problem with F#, I'd love to talk to you, see if I can help. Thank you very much.
That's one amazing talk, and I want to say thank you for this. There's also really good comments in the chat. People saying how they like that this was marked intermediate, but actually is an advanced talk. And I do like your call to action at the end where you say, look, talk to me if you have F# performance problems, because I would love to help. I think it would be great because seeing in this talk that you just bite and keep biting until it's actually resolved is probably the best advertisement that you can make there. So thank you.
Thank you.
Yeah. Yeah, I mean, it's still, again, like, blows my mind. Like, the first thing I'm thinking when I'm watching you is like, you compact it into 60 minutes, but like, how long is this actual journey? Is it days, weeks, months?
A long time. So I think I started this in February.
Mm-hmm.
And then everything through Byte list was pretty fast. I think that was probably about 3 weeks on and off. And again, part of it was that Malti in his talk laid out a really good foundation, right? And so I really suggest people go check out his talk. It is C++, but it's anyone can apply the learnings from there. So he had already laid a really good foundation, and his blog also goes into more detail. So I was very much inspired by that. So I had a general idea of where I wanted to go. So those first few weeks were relatively straightforward. Getting to the structive arrays, and then that final thing, that one hurt. I don't know if I want to confess how many hours I spent on that. But it was, like I said, I probably spent a month of my downtime just thinking about that problem. And I don't have the notebook available, but just like sometimes I've just like written out binary representation of something and like indexing, like, how can I do this? And the solution actually ended up being simpler than some of the other ideas that I had. But yeah, this one took some effort. That last one was painful. I'm not gonna lie.
Yeah, I mean, Martin had I guess he had like a thought too when we were kind of chatting with the group. Martin, do you want to ask that particular question?
Yeah, absolutely. I think it's kind of related to this entire question of how long did it take. We saw that for a long time in your talk, and we were actually saying, okay, the suspense is killing us. We saw that things were being made worse for a very, very long time. Like, when do you generally decides to stop or plow through or say, okay, this is good enough and let's stop here?
Sorry, what was the question there at the end? I'm sorry.
Yeah, that was the question at the end. So when do you decide whether you should stop optimizing because it's a road to nowhere, or keep plowing through?
Yeah, so in my last year when I talked, one of the things I really emphasized is that you should always have a goal in mind. That you should say like, hey, once I reach this level of performance, I'm going to move on and do other things. I didn't do that this time. And the reason was this was more of a creative challenge for myself than anything else. It wasn't like, oh, I have this real world problem and I need something to go dramatically faster. It was more of, and this is why I said like, hey, this is an engineering idea that kind of got out of hand, because it was one of those things that once that bug got in me, I'm like, oh, like, what can I do? What can I do? What can I do? And it was, I have some like pet problems that I like to come back to and just kind of chew on as like, oh, okay, have I learned something that's allowing me to write a more efficient version of this? Do I know a better way to do that? I have a whole nother data structure that I might propose like for next year, which took me years to get the experience to actually understand how to break that problem down and to optimize it. This is one of those. And I've never written a like really proper data structure before. And so, I mean, beyond things like a stack and a queue, like those are trivial. So I was like, oh, this is just going to be a good engineering challenge for myself just to kind of like learn to do this, because I don't have a computer science background. I'm an industrial and a chemical engineer. And I just wrote enough software that they just kind of like pushed me into the software department. So it was basically for my own learning, which is why I kind of gave myself free reign. I wasn't restricted by meeting some business goal.
Yeah. Yeah, the chat is saying, they're saying you had a personal vendetta against FrozenDictionary. That's what drove you. The
That is
madness.
that is not false. That is absolutely not false. It was deeply I was very frustrated with like, how is this thing so flipping good? Um, and it is. And I mean, it is a fantastic piece of engineering. I'm not gonna lie. But when you man, I don't want to say anything. So that approach is definitely an approach you can take where it's like, hey, we're gonna optimize for when we can hash on string length or single characters or all these. I'm like, okay. Um, and I could have just taken that logic and tried to re-implement it in F sharp. Because like, again, I gave credit, like I'm using the .NET's string hashing function like that they use. We're taking out a pointer and doing it like, so that's the hashing function I'm using for strings. I wanted to see if I could beat FrozenDictionary not using that brute force approach of like, hey, we're just going to create a super optimized thing for all these different possible scenarios. And so that's where the idea of having that perfect hashing approach came in. And like I said, if someone recognizes that algorithm, please let me know because I don't want to do the math to figure out the probabilities to write the paper on it. But it's not guaranteed to work. And that's because you could have a case where certain hash codes collide and you just can't get the right bits to differentiate. I have yet to witness that scenario though. So yeah, in practice, it seems to be successful.
Yeah, I mean, throughout this talk, like, do you think the dictionary is the most complex data structure, or is there, I guess, the next white whale in Matthew Cruz'
Yes.
journey?
Yes. It's a priority queue.
Yep. Okay. All right.
And the reason for that is because most of what I do is writing high performance simulations.
Mm-hmm.
I do help with other kinds of code, by the way. I don't just do that, but it's like what my day job is. When I consult, it's for other types of optimization.
Mm-hmm.
But the priority queue in .NET, they decided that if two elements added to priority queue had the exact same priority, they would not guarantee FIFO ordering.
Mm.
So if you add two things, they have the exact same priority, but so you add A, then you add B at the same priority, you could get BA or you could get BA. And in the scenarios that I work in where I need those guarantees, like I actually need this to be in order,
Mm-hmm.
the .NET priority queue doesn't work. And
Mm.
so I have to go and implement one that actually does provide good performance, but also maintains that ordering. So that is my next white whale at the moment. So we'll see.
Yeah. Is that a tease for next year's talk? I
Maybe,
think?
maybe we'll see. We'll see.
I actually was gonna try and nerd snipe you there, because during your talk you dove into x86 codes and looking at
Mhm.
instruction sets and
Mhm.
how things are stored and processed by the CPU. So I actually was wondering, at some point during your entire journey with this dictionary, did you think of hardware intrinsics and looking into that part of the .NET worlds?
Yes. And the reason I sound exasperated is because there, so there are some limitations with .NET and F sharp when it comes to memory layout. Because what I really wanted to do for one of my scenarios is say like, hey, because you're doing this like the hash code equality, right? Just like, well, I have SIMD, I have these additional registers. I could potentially match against several hash codes simultaneously. But to do that efficiently, you need all those values in memory contiguously so that you can do a really quick load. And I really want that as a struct. I really want to embed that in a struct so that it's actually in the backing buckets array. It's not a reference to another array somewhere randomly on the heap. Like that cache hit is just going to be disaster. So like, okay, I want to embed an array in a struct, like a fixed length array in a struct in an array. Like, and that's not easy to do. Now, in theory, you can do it, but you are doing some really janky stuff that, like, at the end of the day, you might get worse performance because, like, the compiler's having to do so much work to guarantee that you're not blowing something up. So that's the real limitation I was dealing with, is because you didn't necessarily have the control over memory layout that you need to be able to really take advantage in those scenarios. And that's where something like C has the advantage, where you can
Mhm.
do crazy stuff like that. And so I'm actually talking at the F# Data Science Conference happening in Berlin on Thursday. And it's all one of the things I talk about a lot is just memory layout. And I'm not going to emphasize the shortcomings of .NET, but this is one of those things where that fine of control really limits you at being able to use the SIMD intrinsics the way you would like to in some of those scenarios. So I did think about it, and it caused me a lot of frustration. And this is where the thank you to the F# community comes in, because they had a lot of patience with telling me, no, Matthew, you can't do that. I'm like, why?
Yeah, I mean, it's funny you're talking about like CPU operations and those intrinsics and stuff like that. Maybe this is a reverse nerd snipe on Martin, but
Mm,
it'd be cool if you could just kind of see it like inlay hinted, like, oh, maybe there could be a different optimization here based on your CPU architecture or something like
mm,
that.
mhm.
Um, so I don't know. I don't think that's coming anytime soon, but I can imagine for folks like you optimizing like data structures, that seeing those intrinsics and seeing what CPU calls are happening would be
Mhm.
really, really helpful, right? When you're
Yeah.
looking at high level code too,
Mhm.
right?
Well,
So
this is why I use sharplab.io quite
mhm,
a bit as a way to see, like, hey, what is this decompiling down to at the end of the day? And benchmark.net can actually do that as well. You can add something on there to say, like, hey, please emit for me all the x86 that you generated for this benchmark, so you can get an idea of what is going on.
mhm. Well, this is like one last question, and then we'll let you go. But you've talked a lot about like x86 architecture and stuff like that. Have you looked at any of the different architectures? Like ARM is kind of the biggest one coming up. Have you tried to run any of the benchmarks on different chipsets?
That's a great question. So I do not have an Apple machine right now, but I have friends who do, and they have run it, and the results are very similar. Now, the
Hmm.
memory bandwidth on the CPU in that iMac Mini is just outrageous. You get the same shape of results. And the reason for that is that at the end of the day, CPUs are all actually relatively similar. And what I mean by that is fundamentally it's a state machine, and it's
Hmm.
mostly made up of loads, stores, adds, subtracts, compares. And so they're not as different as you might think. So y- the answer is yes. I have looked at them. At the end of the day, most of what we are running on is x86 64 CPU, so Intel, AMD's, and it was really interesting to see the result differences between running this on a Zen 2 versus my current machine. But again, it's the same essential shape of the results.
Okay. Yeah, cool. Thank you for that. It's really interesting. So Martin, I'll throw back to you, and then we could say bye to
No
Matthew.
more questions from
Yeah.
my side. So, Matthew, again, thank you for a fantastic talk. I think we enjoyed it. The audience enjoyed it. So, thank you for joining us. And actually hope to see you again next year if we do this.
We'll see.
Yep, me too.
Thank you very much.